Walt Disney Imagineer Asa Kalama. I'm one of the people who design and build all the cool Disney theme park attractions. Like this one, the totally immersive and totally awesome Test Track here at Walt Disney World's Epcot. Test Track puts you behind the wheel of your very own high-speed futuristic test vehicle to experience the exciting and sometimes unpredictable world of automotive testing. And we're talking speeds of up to 60 miles per hour. That's fast. But I know what you're thinking. What does a wild and super speedy attraction like Test Track have to do with science? Well, I'm happy to tell you, plenty. See, as Disney Imagineers, we use science to tell stories to take you to exciting places. And when you start thinking like an Imagineer, you're gonna find that science is really a lot like this. So climb aboard and hang on tight, because we're all tuned up and ready to roll into the wonderful world of imagination, inspiration, and science as we dream it, do it. The science of Imagineering. You guys ready? Whoa. Nobody said anything about crash test dummies. Pretty cool, eh? Welcome everyone to my workspace here at Walt Disney Imagineering Research and Development, the place where imagination meets engineering. And just in case you were wondering, that sputtering and sparking thing back there is called a Tesla coil. I wanted to show it to you for two reasons. One, I'm using it to participate in a really fun challenge that's going on here at Imagineering, which I'll tell you about in a minute. And two, it leads perfectly into the science we're looking at today, and that is electricity. Now, when it comes to electricity, there are a few things you probably already know. We know that we get electricity from our wall outlets, and that it powers practically everything in our homes. Blueberry. We know that it can be very dangerous, and that it's something we need to respect so we don't get shocked. And we know that we can get portable electricity from batteries of all different sizes and shapes. But what really is going on behind this mysterious and invisible energy that makes so much happen in the world around us? In other words, what really is electricity? Electricity is the flow of electrical charge when electrons move through matter. That's right, electrons. Those tiny negatively charged particles and atoms that are always being attracted to their positive proton pals in an atom's nucleus. Get it? Electrons, electricity? Very interesting. Now, in some materials, electrons are very tightly bound to their own atoms, like in rubber, plastic, and glass. But in other materials, like copper and other metals, there are electrons that can actually detach from their own atoms and move towards the protons in other atoms. And so together, these electrons move freely, transmitting electrical energy, electricity, from one point to another. We call materials that easily transmit electrical energy from atom to atom to atom conductors. Materials with tightly bound electrons that don't transmit electrical energy easily, we call these insulators. Which is why most electric power cords are coated in rubber. The rubber keeps the electrons flowing through the copper wire on the inside and not through you. The rubber insulates you from the electricity, so you don't get shocked. Now I get it. If electricity is the flow of electrons from atom to atom to atom in a conductor, how do we get those electrons, those electrical charges, flowing in the first place? That's where voltage comes in. Voltage is the amount of energy needed to move electric charge from one point to another. Voltage, measured in volts, is a lot like the high pressure that's pushing water through the hose and out the lower pressure end. It's like potential energy for each electron that's waiting to flow through a conductor. Lower voltage means fewer flowing electrons. And like this flowing stream of water, a flowing stream of electrons is called a current. Current is how much and how quickly electric charge passes by a certain point in a conductor. Current is measured in amperes, or amps. And 1 amp is approximately equal to 6 billion electrons flowing by in 1 second. That's a lot of zeros. Considering that the power companies supply homes with up to 400 amps, you start to realize that there's a huge number of electrons just waiting to energize all your favorite electrical things. But how exactly do we get electrons to do work for us? To make use of electrons, first you need an energy source, like the power company or a battery. That's where you get the voltage, that potential energy that's just waiting to move each electron. A battery uses chemical energy to push electrons to the negative terminal of the battery. And there they wait, wanting to get back to their oppositely charged positive proton pals through the positive terminal at the other end of the battery.
We wanna move! We wanna move! We wanna move! I'd like to sing!
Maybe later. So to get these electrons moving, you also need to give them a path to travel on. You need a good conductor, like a copper wire, so they'll be able to move freely from one point to another.
Hooray!
But they can't move just yet.
Boo!
We need our electrons to be useful, to do some work for us, to energize a device. Is that okay with you guys?
You got it, Asa!
Once everything is all connected together in a closed loop, the battery starts acting like an electron pump, pushing lots of electrons out the negative terminal, through the conductor, and through the device where they do their work. At the same instant, they're also being pulled back through the positive terminal of the battery to start all over again. We call this completed loop of flowing electricity a circuit. And the work the electrons are doing, whether they're energizing an electric motor in a washing machine, or powering a computer, or lighting a sign, we call a load. And if you want to interrupt the flow of electrons to turn your circuit off, you can always add a switch. Just remember, as long as you've got an energy source, a conductor, and a load all connected together in a closed loop, you have a useful electric circuit in which a current of electrons will flow.
We'll be coming around the circuit when we come, yee-haw! We'll be coming around the circuit when we come, yee-haw! We'll be coming around the circuit making current and we'll work it. We'll be coming around the circuit when we come.
Yeehaw! Yep, nothing beats a big musical finish. As you might imagine, there are gazillions of electrons flowing through countless circuits throughout our theme parks. We're using electricity to create fun and excitement in lots of different ways. Come on, I'll show you. When you think about electricity, you can't help but think about lights. And here at the Magic Kingdom Spectromagic Parade at Walt Disney World, over 1 million are being used to bring everyone's favorite animated Disney characters and some amazingly spectacular floats to life. This is Imagineer Scott Branch. Without electricity, none of this would be possible, would it?
That's right. As you know, electricity is all about flowing electrons. And here at Spectromagic, they're flowing to energize all kinds of different lights and lighting effects. In the parade, we use over 875,000 incandescent lights, 250,000 fiber optic points of light, and 1,096 batteries. To get very specific colors of light, we flow electrons through different semiconductors. We call those LEDs, or light-emitting diodes. We use fiber optics that bend light from the LED light sources we were just talking about. We even have this cool plasma sphere that Mickey uses to bring the parade to life. It uses electrons flowing back and forth in neon and argon gas. But no matter what each particular light does, it's able to do it because of flowing electrons, electricity.
Now, what about these colorful lights that are on practically every float? We see thousands of them during the parade.
These lights with that warm and familiar glow are incandescent lights. They're like the bulbs that most people use at home. They light up and glow due to the resistance that electrons encounter inside the bulb.
Resistance is the slowing down and reduction of electrons flowing through a circuit. We know that voltage is a lot like the pressure that moves electrons forward, and that current is how much and how fast electrical charges move. Well, resistance is a lot like the width of a hose and how it affects the current flowing through it. A bigger hose lets more water through because there's less resistance to the flowing current. A thicker wire also has less resistance. More current and more energy is getting through. A smaller hose lets less water through because there's more resistance to the flowing current. A thinner piece of wire also has more resistance. Less current and less energy is getting through. And a really big fire hose lets even more. I'm okay. So with an incandescent bulb, it's like a 10-lane highway of electrons is suddenly getting squeezed into a single lane.
Exactly. All those fast-moving electrons flowing into the bulb get squeezed through a thin wire called a filament. There's lots of resistance as this happens. Flowing electrons bump and bang into the filament's atoms, turning electrical energy into heat energy. The filament heats up to around 4,000 degrees Fahrenheit and incandesces, which means it gives off light, a very white light. In fact, the only way to change the color of the incandescent light is to literally change the color of the bulb.
Obviously, you don't run long extension cords to each float during the parade, so where does the electricity come from?
Each float and each of our walking Disney characters really is its own complete circuit. Each has an energy source, a battery or battery packs that provide the voltage. Each has conductors, wires that carry electrons to where they're needed. And of course, there are various loads, the lights and the motors that move each unit, and the various onboard animations. But as you can imagine, we don't want all the lights connected together in one long line. If something were to break the circuit at any point, then all the lights would go out. In other words, you don't want a series circuit.
In a series circuit, like on this string of holiday lights, electrons travel along the same path, going from the energy source to light to light to light, and then back to the energy source. If one light burns out or breaks, the circuit would no longer be a completely closed loop. Electrons would stop flowing, and the rest of the lights would go out.
That's why we use a combination of series and parallel circuits on each float. Parallel circuits connect each light in its own circuit to the battery. That way, some electrons coming from the battery travel through one light, some through another light, and so on. Computer-controlled switches in these circuits allow us to turn individual lights on and off in different sequences. And that helps us create the illusion of movement, like turning wheels or flowing waterfalls or moving dragonfly wings.
I know that Spectromagic features around 36 individual floats and walking Disney characters. How do you figure out how much electrical energy each unit will need?
Well, in terms of lighting, we really have to look at the number of lights each unit has, the different types of lights, and how long we need each light to be illuminated.
So we're really talking about watts. Say what? A watt is a unit of power that measures how quickly energy is being used in a circuit.
When designing each float, we definitely wanted lights to glow at different levels of brightness. For example, these are 20 watts, and as you can tell, they're brighter than these 0.1 watt bulbs. When using the same voltage, brighter means more current is flowing through a bulb. So a brighter bulb is using more watts and pulling more electrical energy from the batteries. By calculating the total watts a float needs for the lights, the motors, all the onboard loads, we can figure out how powerful and how many batteries that float needs. And by doing that with every float, you end up with a beautifully lit parade that dazzles and thrills our guests and keeps on going.
And glowing.
Wow, where did you get that?
It's an idea of mine from another episode. Yep, we're still trying to amortize the costs. Get ready. It's time for a shocking but true electrical fact about resistance. Believe it or not, every material has some amount of resistance where flowing electrons are slowed down and reduced. Even we human beings have resistance. And it's because of our body's own electrical resistance that lie detectors work. By running a small harmless current of electrons through our bodies, a trained lie detector operator can see what our normal level of resistance is. But when we lie, we sweat. The salt in our sweat decreases our skin resistance. This allows more electrons to flow, and that's something the lie detector operator can detect. See? No change in skin resistance means I'm telling the truth.
Hey, Asa, have you seen that ice cream sundae that I left in the freezer?
No. Yeah, but at least I feel really bad about it. Kinda bad about it? Okay. It was good. So we saw how Spectromagic uses batteries to energize each float circuit. But at home, most of our circuits use the electrical energy provided by our wall outlets. Our home circuits work like this. The power company is the source. it generates energy by pushing a current of electrons through wire conductors into your home. You complete the circuit by plugging in different loads, like your TV.
Possible that little magnets are made
Hey,
of even
he's not too bad.
and so on and so on.
And your toaster. And your electric-powered feather pillow plumper. What? Doesn't everyone have one of these? So regardless of where your electricity is coming from, a battery or a wall outlet, as long as you've got a source, a conductor, and a load all connected together, you've got a useful electric circuit. But there is a big difference between the way current flows from a battery and the way it flows from your power company. Batteries send electrons in only one direction through a circuit, something we call direct current, or DC. Power companies use alternating current, or AC, which means the direction that the electrons flow constantly alternates, or switches back and forth. And the reason power companies use AC instead of DC is that AC can actually travel much greater distances without losing as much energy to heat. When it comes to AC versus DC, just think of it this way. With direct current, like you find coming from a battery, electrons travel only in one direction. And with alternating current, the electricity coming to your home from the power company, the electrons travel back and forth. In fact, electrons in AC current actually alternate at very high speeds, 60 times every second. It's just a different way of doing things, but both AC and DC are used to make electrons flow. And when electrons flow, you get electricity. From a sea of sparkling Spectromagic lights to a journey beneath the sea, the Finding Nemo Submarine Voyage in Tomorrowland at Disneyland dives you deep into a fantastic undersea world where, once again, that lovable clownfish Nemo seems to be lost. It's also an attraction where electricity is being used in a very unique way to make the submarines move through the water. This is Imagineer Billy Ullman. When these submarines first began operating in 1959 as part of Disneyland's original Submarine Voyage, they were powered in a very different way, weren't they?
That's right. In those early days, they used diesel engines, not very environmentally friendly by today's standards. So when we decided to reopen the attraction in 2007 and theme it around the Disney Pixar film Finding Nemo, we knew it was the perfect time to change all the diesel engines to cleaner and greener electric motors.
But there was a challenge. How do you get electricity to a sub that travels through the water? Safe to say, most people know that water can be a very dangerous conductor of electricity, and that it's not a good idea to mix the two.
You're absolutely right. So to get electricity to the sub without it charging the water, we used an innovative technology called inductive power transfer. It uses magnetism to deliver electricity without it ever actually touching the water.
Magnetism. See, as electrons flow through a wire, not only do they produce electric current, they also produce a magnetic field. So, how does that work here?
On the seafloor of the attraction, under the path that each submarine travels, we have 200 amps of AC current running through an insulated coil of conductive wire.
Wow, that's a lot of electricity.
So there are a lot of flowing electrons in that coil and a strong magnetic field.
And we also have special coils of wire attached to the underside of each sub. The electric current that flows inside the seafloor coil produces a magnetic field. That magnetic field passes through the subcoils, causing the electrons in the coils to flow back and forth. This flow makes AC current that travels from the subcoils through conductors on the sub to charge the onboard batteries. So, we're taking electric current that produces a magnetic field, which then produces an electric current on the sub. Check it out. We're looking into the submarine's seldom-seen machine room, where the electric motor and all the batteries are found.
Right. We have 42 12-volt batteries hooked together in a series. That makes 504 total potential volts, ready to send electrons to where we need them. Our 20-horsepower motor converts some of that electrical energy into mechanical energy to turn the 3-foot propeller, and that moves the sub through the water.
So, in this case, the batteries are the energy source providing the DC current. The wires are the conductor, and the electric motor is the load. Sounds like a circuit to me. It really is kind of hard to believe that you can actually move a giant submarine through the water and into an incredible undersea adventure thanks to teeny tiny flowing electrons. But yes, it's true. There's one type of electricity we haven't talked about yet, but I'm pretty sure you've all experienced it. It's static electricity. Static electricity is the temporary storage of electrical charges on a surface. You get a static buildup of electrons when you rub a balloon against your hair, or pull off a sweater at the end of a cold winter day, or when you drag your feet on a piece of carpet. As you rub your feet, you're actually loosening electrons from the carpet. Those free electrons collect on the surface of your body, where they wait for a chance to jump off towards something with a positive charge. Hey, Josh. Look, I'm really sorry about that ice cream sundae.
Well, that's all right. Ow! Ooh, that darn static electricity. Well, I'll see you later.
See you, Josh. In the name of science, I had to do that. I know, but it sure was fun. Now, most of the static electricity we experience is pretty harmless, because only a small number of electrons are building up on the surface of our bodies. And so when they jump off, the electric current is also pretty small. But what happens when the number of electrons building up on the surface and the current isn't so small? I'm here on the Disney Wonder, one of our spectacular Disney cruise ships, to talk about a very powerful type of static electricity, lightning. Lightning can be dangerous. In fact, it can carry over 100,000 amps of electric current, but it's still caused by a buildup of static electricity. The electrons wait on clouds for the chance to jump to other clouds or to burst downward to get home to Earth where they can connect to their positive proton pals. Yep, there are septillions of electrons and protons in planet Earth. Now, as you might imagine, a cruise ship on open water has to take precautions to keep lightning from causing any damage to the ship. And that's where the mast comes in. The mast is acting as a lightning rod. This is a lightning rod. See, one thing we haven't mentioned about electrons, they're kind of lazy. They always want to travel on the path of least resistance to get from one point to another. Air is very tough for electrons to travel through. There's a lot of resistance, which is why electrons don't jump from prong hole to prong hole through the air. Now, as you might imagine, tall buildings and other structures that reach way up into the sky have to take precautions to keep lightning from causing any damage should they get hit. By placing a metal lightning rod on the tallest part of the building, we're making it easier for those electrons to get back down to Earth. We're also controlling the path they take so they don't damage the building itself or anyone inside. If a ship were to get struck by lightning, the electrons would travel safely through the hull of the ship, down into the water, and back to Earth. So the next time you see a really tall building or tower, or any tall structure, take a close look. See if you can spot the lightning rod. It may be hidden, but chances are it's there. And remember, when it comes to one of our cruise ships, using the mast as a lightning rod is just one of the many ways we make sure our guests are safe and comfortable out on the open sea. So what did we learn about electricity today? Without electricity, we'd never be able to do this. Electrifying. Well, we learned that electricity is really caused by teeny tiny electrons that flow freely to other atoms in a conductor. To make electrons flow in a current and do work for us, they have to flow in a closed loop called a circuit. And for a circuit to be successful, it must have three important elements: an energy source to provide the voltage, conductors to provide a path for the electrons to flow on, and a load, the device you'd like to energize. Resistance in a material reduces and slows the flow of electrons. Resistance not only helps to show when you're telling a lie, it can also be used to make a light bulb glow. And how bright a light bulb glows has to do with how many watts it's using. What's up with that? Static electricity happens when electrons build up on a surface and then jump to something with a positive charge, or back down to Earth. We also saw how electrons like to flow in the path of least resistance. And that's very important to remember, because you never want to fly a kite under or touch a high voltage power line. That strong current of fast-moving electrons will find you to be a much easier path to Earth than through the rest of the power line. And that could lead to a fatal shock. And that's why you should never stick anything into an electric outlet other than a proper electric plug. Otherwise, electrons would flow through you back to Earth. And that too could lead to a fatal shock. Electricity can do a lot for us, But we also need to treat it with a healthy respect so we don't get hurt. And one thing I'm hoping that electricity will do for me is help me win that Imagineering challenge I was telling you about a little earlier. It's a futuristic band challenge that some buddies and I are entering as the all-electric and very eclectic Tesla Coil Trio. See, my musical Tesla coil is all about electrons flowing through a circuit. The coil inside uses high voltage to pull electrons from the Earth. Remember, there are septillions of electrons and protons in planet Earth. Electrons travel very quickly up the coil and collect on the silver donut-like toroid on top. When enough of those electrons build up and the electrical charge is so great, they jump through the air, creating light and sound as they make their way back to Earth to complete the circuit. By using the keyboard, I can make the coil pump electrons at different frequencies, which we hear as different musical notes. But this is only a small part of the Tesla Coil Trio. Let me show you some of the other electrifying stuff we've got planned. Hey guys, this is Claudia and Mark. Mark here is going to play the Tesla drums. Wearing that safety suit, he's actually going to become part of the Tesla coil circuit. The electron sparks will safely flow from the coil through the suit and then out through Mark's feet as they head back to Earth. But please remember, Mark's wearing a special safety suit. You should never try anything like this. As the coil releases electrons, these neon tubes pick up electrons through the air. They will enter the tube and light them up with no connecting wires whatsoever. Pretty cool, huh? Claudia will be playing a guitar that's hooked up to another Tesla coil. As Claudia plays, she'll send a signal, which will be amplified by the coil, pushing electrons, which pulse the air and gives us sound. And I'll be playing the Tesla keyboard and making music with the sparks. But before we start, I have one more attraction that I want to show to you, and it's an electric circuit of a different kind. The circuit I'm talking about is a super fast track. I'm running test track at Walt Disney World's Epcot. I'm experiencing the same thrilling high-speed tests that many prototype vehicles go through. And at the heart of it all is, you guessed it, electricity. Wow!
This is Imagineer Bruce Rack. There's a whole lot of electricity going on here, isn't there?
Absolutely. The entire attraction runs on electricity. Each ride vehicle turns electrical energy into mechanical energy by means of an electric motor capable of 225 horsepower. The 225 horsepower electric motor can take us up to speeds of 60 miles per hour!
So clearly this electric motor needs a lot of electricity.
It's very powerful and operates all day long. You can really feel that electric motor! But onboard batteries aren't really an option
Because they'd have to be massive to store that much energy. And that would weigh down and slow down the vehicle. You came up with another solution.
If you notice, there's a slot that runs down the middle of the entire track.
We're following the slot in the track.
Under the track are long strips of copper we call bus bars. They're actually giant conductors that carry electrical current along the entire route. Each vehicle has metal collector shoes that slide along these bus bars. So to move the vehicles around the track, the electrons flow from the power source through the bus bars into the collector shoes and to the motors that power the vehicles.
Woo! Feel the power of electricity!
Here we go, up to 64 miles an hour!
The electricity also goes into energizing the sound system, the vehicle's lights, as well as the onboard computer and video displays.
And because more than one vehicle is connected to the bus bar, this is another example of a parallel circuit. And speaking of circuits, I was thinking about taking another ride around the track. You up for it?
Sure!
And now, the all-electric and very eclectic Tesla Coil Trio. 1, 2, 3, 4. Awesome, guys. I hope you'll remember that everything starts with an idea. If you follow through with your ideas, science can be the means to turn them into reality. As we say at Imagineering, dream it, do it. You guys ready? 1, 2, 3.